if it's visible. Thank you. Okay, before we get started, the agenda for the day is to understand RNAs in detail. So today's session is comparatively a bit complex. Here, different kind of RNNs that are available, whether it's group, LSTM, or some other RNNs like bidirectional RNNs, how the gradient descent works in RNN. Okay, so that's the agenda for the day. So before I get started, a brief from yesterday. And then before I start, there are some reference slides that I'm going to, which are from Andrew NG. Okay, these are some reference slides which I am referring to. Okay, so now we have talked about RNN, what an RNN is, why we should use an RNN, and how an RNN works. Basically, this is one of the simplest example of an RNN, which is a many-to-many RNN, जहां पर आप एक सेंटेंस पास कर रहे हो. ये क्या है? ये आपका एक सेंटेंस है. अंडरस्टैंड इट लाइक दिस. मान लो आपके पास 10 ट्वीट्स हैं, हर ट्वीट अपने आप में एक सेंटेंस है. तो आप मॉडल को पहला सेंटेंस पास करोगे तो ये पहला सेंटेंस है, याद रखो. x1, x2, x3, x4 ये सब क्या है? आपके पहले सेंटेंस के वर्ड्स हैं. ये मान लो उसमें लिखा है कि I went to उदयपुर. सो it will be like I went to so each of these X is one word of that sentence. Remember that. Okay. So whenever you are doing natural language processing, that means there is a sentence and a sentence have words. So words have an order. So that means that order needs to be preserved. So what you want is you want to pass these features in an order, in a time-based order. Consider a simple neural network, which is like this. And then it is just passing on maybe to another layer. Okay, maybe another layer. The point is, why I am not using a simple neural network, right? I can also have like I went to say Udaipur. This is like one record. One record is nothing but one sentence, right? Which is I'm passing into the neural network. I can use it like this also. Like each word is a feature, as I was talking in naive bias, right? But the point is, when we were doing naive bias, we were interested in classification. Okay, means at that point the order was not important for. But now I am not doing simple natural language. I am doing some prediction, as in what word is going to come next in this sentence. What is the missing word? Okay, what is say for example converting machine translation. Okay, then the order matters, right? So when the order matters, I cannot use even a network like this, because this is a simple MLP, a multi-layer perceptron. I could have used this, but when I pass the words in these nodes, when the data propagates through a MLP neural network, the order is not preserved, okay, during the processing through a MLP. Okay, whether this word comes first, whether this comes first is not preserved. So that's why I cannot use a multi-layer perceptron. Rather, I need an enhanced model, which is an RNN. Okay, तो पहले इतना तो क्लियर है कि हम जब नेचुरल लैंग्वेज की मॉडलिंग करेंगे तो एक सिंपल न्यूरल नेटवर्क क्यों नहीं काम का, क्यों हमें यहाँ पर RNN पे आना है. Okay. Now we looked at this particular RNN, this one, which is a many to many. So RNN can be of multiple types. I told you, it's like many to many and many to one, which is like primarily the most famous ones. Many to many में क्या होगा, जैसे कि मशीन ट्रांसलेशन हो गई कि आपने एक वर्ड भेजा, मशीन ने उसका कॉरेस्पॉन्डिंग कन्वर्जन कर दिया. आपने दूसरा वर्ड भेजा, मशीन ने उसका कॉरेस्पॉन्डिंग कन्वर्जन वर्ड दे दिया. आपने तीसरा भेजा, मशीन ने उसका कॉरेस्पॉन्डिंग कन्वर्जन कर दिया. राइट. तो एक तरह से ये आपकी एक लेयर ऑफ न्यूरॉन्स हो गई. अगर आप वैसे देखें, ये आपके न्यूरॉन्स हैं और ये एक लेयर ऑफ न्यूरॉन है. बट यहाँ पर ये जो न्यूरॉन्स हैं, they are not like independent of each other. They are connected. You can consider it like this. MLP में it used to be a layer, right? This used to be a layer, and then you may have another layer. But these neurons were not talking to each other. Here, consider that these neurons are like talking to each other in a time-based fashion. That by 2 सबसे पहले है T0, T1, T2, T3. So you can develop that kind of intuition between this and this. Okay. And then you are getting certain outputs from these neurons at every time interval. Okay. But the point here is, whenever you are even predicting anything from a neuron, there is an, other than input, there is some memory which is coming in picture. You have stored some knowledge that is coming in picture. Obviously, to start with, you won't have any knowledge, or you can initialize initial value, as we say. But later on, at these points, there will be some output which will be stored in memory, so that if anything is generated by this cell, it will be used in the decision by this cell, which we saw yesterday. So this is like your RNNs. RNNs are like your go-to models for natural language modeling, and these are their architectures. Many to many can have one more architecture like this. You can look through, where what happens is, through initial neurons you don't get any outputs. Okay, it just they keep on generating the intermediate memory information, and then later on there are certain cells which does not take inputs, but based on the past, whatever the memory is being passed to them, they start to generate the output. But again, it's like many to many. That can be again machine translation, converting from one language to another. Many to one, as I was telling you yesterday, is where you pass on too many words. Just consider many means many words. You are passing too many words and getting one single word as output. So that means tagging an article, right? Or sentiment analysis. You are passing too many words to tell you the sentiment. You're passing too many words to tell you which genre this music belongs to. You pass a song, and then output is whether it's jazz, whether it's metal, or some other genre. So that's like many to one. You are passing many words to get one output. But I told you yesterday that just hold on to one to one, one to many, because that's primarily not used much. However, what happens is, in one to one or one to many, let's understand, one to many is what? Passing one word and getting many words output, which you have to. Can anyone think about a scenario words as output. What kind of requirement will that be? Okay, let's go one by one. Let's go one by one. Many to many में आपके माइंड में और क्या एग्जांपल आता है? नहीं, many to many. So for one to many, you are saying synonyms. Okay. So you are passing one word and you are getting many synonyms. Yeah, Nishtha, correct. Search engines, okay. Translation of a sentence. Okay. Translation of a sentence, Rahul, I will say it's many to many. Because many to many में ऐसा नहीं है कि आपने 100 वर्ड बाहर भेजे तो 100 ही बाहर आएंगे. हाँ, अच्छा 100 के कॉरेस्पॉन्डिंग आपको 50 भी आ सकते हैं या 500 भी आ सकते हैं. But it's like many inputs and many outputs. Okay, Rahul, yeah, you are correct. Yeah, so one to many में जैसे synonym is one of the example. But consider it like your model is so smart that you ask it, you give it a word like thriller, and it writes a story on thriller immediately. You are asking a model write a story on thriller, so you give one word and it writes the output. पूरा एक sentence निकाल देता है पूरा. Yeah, you ask it to generate a new music. So passing in a single word, maybe you give it a genre, it generates the completely new music for that one to many. Okay. So that kind of things. So Karan, one to many passing name of a person to get his details. This is a normal search. You really don't have machine learning there. Like passing the name of a person to get his details. It's just a simple lookup. You can just do a lookup. You don't need machine learning there. Machine learning is when something new happens. Okay. So that's like one to many. One to one is again like not that defined as such, but yeah, you can say for one word you are getting another word as output. You can think about that example. I haven't used it, but there must be some practical examples for that also. You pass on a word, you get another word as output. So that's like one to one. Image captioning. Okay, yeah, Pragesha, I'll take that one to one like image captioning, but the point is the input is a single image, but internally that image breaks into smaller features to give you the output, right? So I want you to think from the feature point of view that you're passing one feature to get one output, because image itself will be split it into multiple pixels, or I would say sections. But yeah, I think that's fine for now. Image captioning is one, or there may be some other examples to this. So these are some of the RNN types which you should basically be aware about. This will help you to understand that the kind of problem you are solving belongs to which of these architectures. You are not building these architectures, but these architectures are already built by people. So as for your knowledge, like how they really works. Okay. There are like definitely few interesting things in these architectures if you look at one to many, because there is only one word you're passing in. So these multiple neurons, I would say time separated neurons, right? These are time separated neurons. एक उनके multiple copies हैं at different times. ये ऐसा नहीं है कि 100 अलग-अलग neurons how that happens is, if I'm saying something like, say, lazy fox, right? Lazy fox, for example. So what I mean to say lazy, jumps, that's it, jumps over, right? Jump over a cat. Simple. Okay, just keep it that way. Now the point is, if I want to identify this particular word, like what this particular word is signifying, or what this particular word is signifying, whether it's a noun or it's a place or a product. Now the RNN is a forward RNN. It's a forward RNN, as in, for this, if I have to predict anything, whether it's a noun or not, let's say this is saying it's a noun, okay, I only have the previous cell information, the previous word, that can help me to decide it. Okay. Or maybe for this particular word, I have a previous word at max which can pass on some information for this particular word. Okay. So the problem here is at any given word, only the previous word can help me to identify context, but not the ones that are after that. Okay, so this is known as a unidirectional RNN or a bidirectional RNN. There are bidirectional RNNs also, which are known as BRNNs, bidirectional RNNs, which is another class of RNNs, which not only takes the previous but the next also while taking some prediction. Okay, like tagging it as something. Okay, whether it's a singular, plural item, whether it's a place, because sometimes fox, I want to see whether it's an animal or I'm talking about, say, Megan Fox, which is an actress. So how can I know that? I can say, okay. So guys, if you look at this screen, so here I'm still in the RNNs. Okay, I'm still talking about RNN and how the RNN is doing the gradient descent, right? Again, so the gradient descent that happens in RNN, is actually again back propagation, but it's known as BPTT. BPTT means back propagation through time steps. Back propagation through time steps, because here this is one RNN cell, there will be another RNN cell, you go in the forward direction to train the model, but your gradient descent happens in the backward direction, right? It's like back propagation. You adjust the weights at this layer first, then you adjust the weights at this layer, then you adjust the weights at this layer, right? Now, when I say you adjust the weights, you already know that when you are connecting from this neuron to this neuron, there is a weight, right? There was some weights I was talking about always. And even the input that is coming here, that also have a weight, right? So the input which was coming here, the input X was having a weight, and the hidden state, the memory state which is passing, also had the weights. Okay, so there are these weights, right? There are these weights that I need to adjust. So I need to minimize my cost function again, this cost function. So there will be a cost function that you need to minimize using the backpropagation in a fully connected neural network because of all the connections happening here. I need to do the partial derivative with respect to the activation function. Again, the chain rule of differentiation or partial derivative. But this activation function will be partially derivative with respect to the three main weights. The weight x, which is like coming here, wx, the weight of a, which is the weight of the hidden state connection for the loop. And this is what? Can anyone tell me? What is this? Please ping me. What is this? So at any RNN cell, there will be three weights: a input weight, a hidden state weight, and a bias. Very good. So that's what the whole equation is. If you look at here, so ये थोड़ा छोटा सा दिख रहा है यहाँ पे, but yeah, you are ultimately doing the partial derivative of cost function with respect to weight, which is input weight, the hidden state weight, and the bias. And that's what a chain rule is. And these are the three values which are cached at every state. Means at any cell, if I talk about its memory, at any cell, I talk about its memory. So which information will it have? It will ultimately have जो पीछे से उसके पास a of t minus 1 आ रहा है, जो पीछे से एक्टिवेशन स्टेट आ रही है, हिडन स्टेट आ रही है, उसकी खुद की जो एक्टिवेशन स्टेट है या हिडन स्टेट है, और जो उसको इनपुट दिया गया है. ये तीन मेन पैरामीटर्स उसके कैशे में हमेशा रहते हैं किसी भी आरएनएन सेल के. So this process is known as BPT in RNN. So so you guys can really go through it. But if you look at like this is what I have been telling you. If you have a good look at it, that these are your RNN cells, and each RNN cell will have a certain input. So a weight there, then some initial state, and a weight there, and then it generates its own activation function like that. But definitely there will be some errors which will be associated. So we have to minimize these errors, and definitely these errors have different formula in terms of natural language processing. There is something known as perplexity parameter, which is computed. But yeah, so this is how the backpropagation really happens here. So if you look at, let's say your system builds an error function, a cost function, which is yt log of yt, okay, one of the error functions that is being built, then you are doing what? See, ultimately this is the input that passed on to the network, the neuron or the RNN cell. This is the output that got generated, right? So these are the outputs that got generated. So the errors will be with respect to the words or the output that are getting generated. You will do the summation of all the errors. That's one of the error function, and the purpose is to ultimately minimizes that error. And how we do that is we do the partial derivative of the cost function with respect to the weights, whichever weights are available in entire process. Okay. But here, it's not only one single error that you are uh, doing backpropagation for. Rather, these are time steps. These are known as time steps, right? Time step 0, time step 1, time step 2. So you do the backpropagation. You start from here all the way. It's like these arrows are actually signifying which particular weights you are adjusting, which particular weights, all the weights that you are adjusting while doing this process. So these are all the weights. Okay, these are all the weights that we have been seeing, the weights with the inputs, the weights with the activation function, and even the weight with the final output that is there. So this is not backpropagation, rather this is backpropagation through time or time steps, but it's one and the same thing. Now, the problem with the RNNs was the vanishing gradient descent, as in why was that? Like they were not able to converge. You understand it like this: they were not able to converge to the local minima or the right point, because first of all, they were only talking about one step in the past. Okay, so they were not really able to look to old values in the past. If you could have looked to old values in the past, your gradient descent, instead of getting vanishing, मतलब गायब होने की बजाय, it will converge because it's able to now look up at much older values to take certain decisions. And that's where the whole idea for the advanced neural networks, RNNs, came in picture. How to solve the problem of vanishing gradient descent, and further how to look up in the past rather than just one previous value. So that's where these two, GRU and LSTM, came in the picture. So before I go into that, let me check this. Yeah, okay. So now what happened is GRU came later. LSTM जो है वो पहले आ गया था मॉडल, बट अभी रिसेंटली GRU को बहुत ज्यादा अडॉप्ट किया जा रहा है, और हम कह सकते हैं GRU जो है वो LSTM का एक सिंप्लीफाइड वर्जन है. LSTM is more complicated. GRU is comparatively easier to understand, and it's widely adopted nowadays. So before we go into LSTM, let's understand GRU. This will help us. And GRU is a recent model. 2014, I think it came in, yeah. So again, let's see how the architecture for GRU is modified so as to take past values in consideration. So this is the best example. This is the best diagram that you can look at. What this doing is, again, like ये एक RNN cell होता था, अब ये GRU cell है. This is not an RNN cell, okay? What is it? It's a GRU cell. In the RNN cell, if I talk about RNN cell, अगर मैं इसको RNN में convert करूं, तो यहाँ से आपके पास input आता था, यहाँ से आपके पास एक hidden state आती थी, right? And then यहाँ पर आपके पास एक single activation function होता था, एक single activation function होता था, okay? जिसमें क्या होता था, पहले तो इन दोनों का समीशन होता था, right? मतलब this input multiplied by its weight plus this input multiplied by its weight, whatever it is. they used to first do the summation and then it used to pass in the activation function, which primarily used to be 10H, right? 10H. Okay, so that used to be your RNN cell, but now here it's modified, means 2 additional cells are introduced. That means ये 10H तो अभी भी रहेगा, but before that 10H, these two outputs, right, which are coming in, they will actually be going inside this. How? That we will see. So let's see an RNN पहले, just to keep it clear. So as we have even seen yesterday, if this is an RNN block, guys, if this is an RNN block, what used to happen was, this is your input X at the time t, and this is the hidden state or the memory which was at time t minus 1. Both have their own weights. They were multiplied by their weights and summation happened, and then the activation function ran, and you got the output value. You got the output from here, which was your this thing h of t. Okay, so this was your h of t. But while calculating this, there was this bias also. Okay, there was this bias also, which was being added. And from this activation output, this is the h of t, this thing, just focus this h of t, which was coming as output from here. The same h of t was actually being passed to calculate this also. Here y of t is a separate thing. Okay, this is another formulation of that. वो पुराना वाला जो था, ये वाला थोड़ा उतना आई वुड से उतना एक्यूरेट नहीं है, बट अगर आप यहाँ देखें तो दिस इज अगेन व्हाट आई हैव बीन टेलिंग यू, यू आर मल्टीप्लाइंग इट विद इट्स वेट, जो हमने कल देखा था. ये एक एक्टिवेशन है, प्रीवियस एक्टिवेशन वैल्यू मल्टीप्लाइड बाय दैट एक्टिवेशन वेट, व्हिच इज दिस bias term which get added, and then 10H, and that 10H will give you the activation function which is going out, and also this is going into the next neuron which may do a softmax or something for its own computation. But main is this a of t, always remember. So this is nothing but 10 of h on this particular formula, जो simple neural network में भी होता है. somewhat वैसा ही है, मतलब ये you have time steps, that's the only important thing. previous जो neural networks होते थे उसमें जो previous neural networks होते थे, अगर आप थोड़ा रिकॉल करें तो वहां पर x1w1 x2w2 like that, if multiple features are going in this particular cell, तो इसकी जो समीशंस होती थी वो क्या होती थी, x1w1 x2w2 x3w3, वो इसका समीशन होता था. वो यही तो होता था, और प्लस उसका बायस. लेकिन वहां x1 x2 x3 होते थे. यहाँ पर सिर्फ एक इनपुट है, एक मात्र इनपुट है, एक बायस है और एक प्रीवियस एक्टिवेशन वैल्यू है. तो बस ये भी समीशन ही है, और उस समीशन के ऊपर यहाँ पर फिर एक एक्टिवेशन फंक्शन लगता था, सिग्मॉइड, रीलू और समथिंग. तो वही हम यहाँ लगा सकते हैं, sigmoid, relu, 10H. It's similar things. Okay, but definitely this is not the output. The output will be this y of t, as in ये एक एक्टिवेशन वैल्यू, एक इंटरमीडिएट वैल्यू है जो आपकी इंटरमीडिएट लेयर्स को पास ऑन होगी टू टेक डिसीजन. बट ये जो है ये आपका एक्चुअल फाइनल आउटपुट है, as in you want to predict sentiment. Okay, तो या फिर एक वर्ड को दूसरे वर्ड में आपको कन्वर्ट करना है. So that kind of things if you have to do, तो वो काम यहाँ से होगा जो फाइनल आउटपुट है. Okay, so from here you will get that final output y of t, which will again be what, because this data is passing to this another neuron. Say consider this is a neuron, so there will be a weight. So a of t multiplied by that weight, plus here also you have some bias, and then you will have the activation function which is available here. So far is it clear, guys? So far is it clear? Is this making sense? This is what we have been discussing. Because this is complicated, I want to go as simple as I can make it for you guys. So always related to the old neural network. I have pinged you this. This is quite good. You will not get this diagram everywhere. Okay. So this is about it, the RNN. Okay. So now, since you are now having this in mind, you can try to understand the another architecture. Let me open that simultaneously. So now, since RNN cell is quite clear to us, we will go inside the GRU cell. So let's look at this, the GRU cell. Okay. अभी क्या हो रहा है, हम इस सेल को धीरे धीरे बिल्ड करेंगे. अभी ये इनिशियल स्टेट है सेल की. अभी नेक्स्ट इस डायग्राम में ये और बिल्ड होगा. दिस इज अ GRU सेल. कई बार क्या होता है, आपको इंटरव्यू में ये डायग्राम दे दिए जाते हैं और नीचे 4 ऑप्शन होते हैं कि भाई ये कौन सा सेल है, ये एक RNN सेल है, ये GRU सेल है, LSTM सेल है, या फिर ये एक बेसिक न्यूरल नेटवर्क है, व्हाटएवर. तो इफ यू नो अबाउट दिस, इवन द नेम ऑफ द गेट्स, यू विल बी एबल टू डू दैट कि भाई ये क्या है. ये आपका मैंने बताया था रीसेट गेट और अपडेट गेट ये GRU में होते हैं, जबकि LSTM में 3 गेट्स होते हैं. याद है किसी को LSTM के 3 गेट्स का नाम? एनीवन? LSTM में जो 3 गेट्स होते हैं, एनी आइडिया? या हर्षिता करेक्ट? Yes, Aditi, correct. So input, output, and forget gate, right? Yes, yeah, Gomini. Very good. Thanks, guys. So this is even if you know these things, they are more than enough. As in just to pictorially understand it, not in detail. So now to go in detail, what happens is here also the same thing. You have an input, you have a hidden state. Here also same thing. You have an input and you have a hidden state. Right? No rocket science. But now this internal picture, let's see how it changes. Here you have that 10H. उससे पहले की पूरी जो महाभारत है वो तो होगी, इसमें तो कोई कॉम्प्रोमाइज ही नहीं है. बट ये 10H जो आपका फाइनल एक्टिवेशन जनरेट कर रहा है, उससे पहले क्या क्या होगा वो थोड़ा इंपॉर्टेंट है. तो विल सी this reset gate and update gate, how they play a picture. So here we have 2 gates before the final activation function. Let's put it there. So these are sigmoid. Sigma means sigmoid functions. So these have their own activation functions, sigmoid functions. Okay. So that means there will be a weight which will be for this W1, and then there will be a W2, there will be a W3 and a W4. Just remember that all the connections will have their own weights. 4 connections means 4 weights, and that's what even your backpropagation will do when it will start adjusting it. Initially model will start with some weights, or you can pass on a weight vector but then model will try to back propagate and adjust these weights. It may be a back propagation or it may be a back propagation through time steps. That's the only thing. Everything is a chain rule of partial derivatives. जितने ज़्यादा parameters उतना slow आपका model, right? That's we have been talking about, right? That's like another thing. Okay. So let's see this. So we know that there will be 4 weights, and all of them will be going inside the sigmoids, which are the activation functions. But before that, there will be summations that will happen. So let's see what happens. So if you look at, guys, very simple. Here what you see is very easy. The output from the reset gate will be the activation function sigmoid on top of the input, this thing, plus the weight which is associated with it, which is x of r. X means input, r means reset gate, x of r, plus again h of t minus 1 जो कि यहाँ से hidden state आ रही है और उसका अपना weight होगा with respect to r. Simple. And then there will be a bias with respect to this gate. Okay. Similarly, this is also very easy. What is this? This is the update gate. So the update gate will generate another value, which is sigmoid of x of t, weight of this, again this and this. You will get 2 values. But अब बात है कि इन 2 values का मुझे करना क्या है वो हम देखेंगे. But before that, everyone understand this formula? Guys, yes or no? Reset gate and the update gate. Okay, perfect. So we are computing the reset gate and the update gate in the GRU model. Okay, so that's what the GRU model is. So let's now deep dive to the next step. So here we have enhanced that model a bit. We have introduced the 10H, right? That's what I was telling you. Yes, Gulzar, RT is the reset and ZT is the update. So we don't say U, we are saying Z. It depends on the scientist to scientist. Like some people may use U for update gate, some will use Z. It's for different researchers. Okay. Yeah. So this is the formula. I'm sharing this link also. So there are some good things like Andrew Ng's papers or this particular website, this d2l.ai. These are some reference things that I'm taking in. These are really good. You don't need to jump to internet much. Just look at these things. Okay. So are we good, Gulzar? Perfect. Thank you. But now the question is, the final output that I need, right? The final output that I need, where will I get that, right? Because the final output will come something from here, which will be what? H of t, right? The hidden state, H of t. Some people will say it A of t. Okay. Some say H of t. So here someone will say A of t minus 1, which is like activation, previous activation. So that's not a problem as such. So I need this, right? So this will come from what? This will come from another activation function, which is primarily a 10H function. Okay. And then this data which we have should pass on or will get computed along with this. Okay, so it may also generate something. So all these 3 will together take some decision. So let's see what that is. So now if you look at here, so guys, now what happens is we put the 10h function, which is the actual thing, and we again pass on the input. If you see, the input is coming in here, the input is coming in here, but now along with that input, this hidden state which was there, the previous state, right, that is not being passed like as is. There is some reset gate which have been applied to the hidden state, and this particular operation here signifies a vector multiplication or element wise operation, as in, like if you have two vectors like say A and B here, so you will multiply this element by element. So that's how this kind of symbols are. We will see that in the next screen also. But now this reset gate is going to take a decision or help in taking a decision on this hidden state, like whether the previous hidden state is really that important or can it be overridden. So यहाँ पर क्या होता है, ग्रू गेटेड रिकरेंट यूनिट्स में हम जो हिडन स्टेट्स बनाते हैं, हम ब्लाइंडली उनको यूज नहीं कर रहे हैं, पहली बात, क्योंकि पहले हम क्या करते थे कि सिर्फ एक ही प्रीवियस स्टेट होती थी, उसको यूज करते थे. अब यहाँ हमारे पास जो भी स्टेट है उसको हम एक इंपॉर्टेंस देंगे कि क्या उसे सही में यूज करना है या नहीं करना, कितना यूज करना है, और क्या उस स्टेट को अपडेट कर देना है. Okay, so there are certain important things. So here if you see, the output state that I'm generating is a candidate hidden state. It's not the actual which is going out. See this 10h value ideally should have been thrown out of this cell to the another cell, but it is not done because we are saying it's still a candidate. It's not, a decision is not yet taken whether this is really should go out as is और इसकी जो वैल्यूज हैं उनमें कुछ मैनिपुलेशन करना है, मतलब इसका 10% ही आगे भेजना है, इसका 20% ही आगे भेजना है. गेटिंग इट. पहले क्या होता था, एक तो ये पूरा का पूरा यूज हो जाता था और दूसरा ये पूरा बाहर चला जाता था. अब ये बाहर जाए, कितना इसका फैक्टर बाहर जाए, ये कितना अंदर यूज हो, कितना इसका फैक्टर यूज हो, ये कुछ चीजें हैं जो अब एक ग्रू ने टेक केयर की. So let's see first of all how h of t is calculated before we go deep dive. This is element wise operator जो मैं कह रहा हूं यहाँ पे, ये element wise operator आपको signify कर रहे हैं. So the hidden state formula here, the hidden state formula, where is it? Yeah. The hidden state formula here takes this particular form. What do you mean by that is, you see this tilde here, right? This tilde is the candidate hidden state. The candidate hidden state. This is the previous hidden state. Okay. So we will do this and this vector multiplications, element wise multiplications, add it as in before identifying the final output h of t. We are coming to that, user. So that means this z of t is playing a role as in if the value of z of t is what, let's see. So z of t is your update gate. So this update gate is very, very important. This update gate says भैया ये आपकी करंट स्टेट है, जो कैंडिडेट है, ये प्रीवियस है. अब जो बाहर जाए, what should go out? So we will use a sigmoid value. Okay, we will use a sigmoid value, and you know that sigmoid curve is like what? A sigmoid curve is something like this. Okay, something like this, not exactly like this, means its value will be either 0 or 1 somewhere. Most of the time it's zeros or ones. In very minor range it's between a few other values. So that means this update gate will help in deciding the output. How? Let's see this. So if you see that you have a candidate state and you have a previous state, then the current state should be z of t and 1 minus z of t. Now if the update state is saying 0, this will be of no use. The previous input will not be used. The candidate value will go out. The candidate value will go out. But if this is 1, if this is somewhere 1, that means the output will be the previous state. You have to use the previous state, not the current state. And however, when it's in between these two values, most of the time you use a combination of both of these, some part of both of these, as in you are learning from the past also and giving the output. We will look through this formula once again. Let's see how h of t is getting computed then. This h tilde t. So now the h tilde t, the h tilde t, the candidate state, which is the most important part, which is actually this thing. I told you it passes through a 10H. It's passing through a 10H. But what are the inputs to it? So मैंने स्क्रीन थोड़ा छोटा कर दिया है जैसे to keep both on the same. So if you see, you need this candidate state. So this candidate state is being computed. First of all, activation function तो हमने लगा दिया, but x of t, which is this x of t which is coming with its own weight, wx of h, plus ये bias वाला part, which is something from here, another bias. But now if you look at this, okay, so how I'll tell you this is, it's like this hidden state. Okay, consider it like your hidden state is coming with some weight, is coming, and that's how the summation is happening. But now with hidden state, this reset gate, okay, this reset gate is doing the element wise operations to help you in doing certain stage resets, which will come to know. 1 minute. Okay, so that same thing which I have told you so far, I'll again recap that, whatever you have seen so far, with another example. So whatever you have seen so far, what was happening there? This was your groove cell. Okay, this was your groove cell. You're passing in an input. Okay, you're passing in an input to this thing, which is the update stage. We will talk about the reset stage later. So just keep it side. So we are talking about the update stage, and then we have this 10H stage. Also, we have a concept of memory cell. Okay, that means, as normally other cells have, so groove cell have some memory, and that memory is nothing but the output that it's generating, the activation output, not the y of t. Okay, that's not y of t. So that means this memory cell will always have a value of the activation. Okay, but now what you have to calculate, like to reach up till this particular value, you have to go through certain computations. So that computation is, we first calculate the candidate state. किसी भी ऑर्डर में कैलकुलेट हो सकता है, so don't worry about it. बात है कि वो सब आपस में कंबाइन कब होंगे. So if I have 10 of H, so what I'm doing here is I'm calculating the candidate stage using activation function and this formula. This formula and the previous formula is same. It's just a vector representation of that formula, where what I'm doing is I am passing on this X, which is input, multiplying by its weight. So here what this signifies is this particular thing multiplied by this plus this particular thing multiplied by this, where this WC is actually a weight vector. So again, to keep it simple, your 10H function will generate a candidate state, which is this. And this candidate state is actually going to be taken as the current state value, is groove cell ki value. But then there is some other formulas that will help you to take that decision. So we will use the update gate, and now the update gate is a sigmoid gate. You will see here it's a sigmoid function, and again here it has its own kind of calculation. So you calculated the reset gate, update gate, and the candidate gate. अभी तक यहाँ तक clear है, up till these three things? So if you look here, we have calculated the updated state, the reset, update, and the candidate state. Just don't look at the reset gate right now, it will be confusing otherwise. Now what happens is, the actual value of the memory cell. So if this is your memory cell, which is A of t, मेरा पूरा पर्पस है ये वैल्यू निकालना, which is nothing but this value. Now this value is based on a formula, and this formula is used just to avoid the problem of vanishing gradient descent. Because पहले क्या होता था, आपका जो C of t निकलता था यहाँ से कैंडिडेट स्टेट, वही एज इज इसमें चला जाता था. but we are not doing that. Okay, based on the past values, like I want to look up too many values in the past, there is some sentence, and using this sentence, say I may have to take a decision at this particular value, that this, like we are talking about something which is being eaten here, right? Food, right? We are talking about something, food. So I have to take some decision here, but I don't want only this. Rather, I want all the past values to help me in taking that decision. Or for example, this particular word, I want to take decision based on all the past values which are there. So that means I need to give some importance to the past values in the order of maybe some decreasing order. And for that, I need to have certain gates, which are like update gates and the reset gates, which will actually help me to update those values. So here what I'm doing is, this C of t here is not only the candidate state which is coming from 10 of h, rather I am multiplying it with the update state or update stage. उसकी वैल्यू 0 और 1 के बीच में रहेगी, जो मैं आपको बता रहा हूँ सिग्मॉइड फंक्शन है, मोस्टली 0 और 1 के बीच में रहेगी. तो अगर आप इन जनरल सोचो कि अगर अपडेट गेट की वैल्यू हमेशा 1 होती, अगर हमेशा 1 होती, तो ये एक नॉर्मल आरएनएन होता. ओके, अगर वो हमेशा 1 होती, इट वुड बी अ नॉर्मल आरएनएन, बट हियर वी आर नॉट डूइंग दैट. So here what we are doing is, we are computing a new value. We are computing a new value using definitely the past value. Definitely the past value is being used to compute this new value. But पहले हम इस new value से खुश हो जाते थे. But अब हम ये भी देखना चाहते हैं कि क्या past value का significance still hold करता है, क्योंकि इसकी computation में तो past value use हुई है. But does the past values still have the relevance? That's what it is actually doing, because that will be decided by the update gate. Now update gate will take a value as, again, 1. That means it's only and only talking about using the candidate state. But if it is 0, it's saying no, don't use this value, as in you have this memory cell. Okay, as in you have this memory cell. So initially this memory cell also have a value of say ct minus 1. So do I really need to update it or not? That kind of decision is being taken here. So if this update gate says 0, you really don't need to update it. You keep it as is. What is coming from the past, just keep it here. Okay, keep it here. But no, you say I have to update it. So you will say, okay, no, remove this, update it completely with this new value. But you say, no, I will fall somewhere in between, like somewhere in between. So some contribution of the past, some contribution of the present, both will be used. So it's all about the current memory state, whether you want to update it with a new value, you want to update it with a slightly modified value, or you want to keep it as is, which was coming from the past. This is what the update gate tells you. And the reset gate actually further helps you to control that to certain limits. It further helps you to control it. But yeah, again, I'm not going into much detail. It will be confusing, but tell me, Is it clear so far? The formulas, I'm asking about these formulas are clear because you will see these formulas everywhere. Or you want me to repeat? I'm fine repeating it. Guys, are you fine or you want me to repeat it? Okay, I'll take it as repeat. Yeah, hai, Gulzar. No answer means I'll repeat it. So let's look at here. For example, let's talk even about this particular thing. So there is this sentence, and this sentence you want to do some natural language processing. Maybe you want to identify all the entities, like cat is an entity here, for example, right? Then you may want to do some fill in the blanks, like some word which was missing, maybe like this or some other word, maybe or this. You want to fill in that word by looking at the context. Okay, so you have to do that kind of operations. So what you will do, you will create the RNN cells or the GRU cells, right? You will create the GRU cells, or your model will create the GRU cells. These values will be passed on here. Okay. But now, for example, if this was the word you have to fill in, you may not only be satisfied with the past word or the knowledge. You want that knowledge to be passed on all the way from, say, the first word, or also from this. You want all of these to contribute, all of these to contribute. So you need a long-term memory kind of, not a short-term memory. So GRU will help you, or LSTM will help you. How they will help you is with the help of certain formulas, where what will happen, say you have to do this prediction from this, like what this value should be. So for that, you have to explode this cell. So let's say I'm exploding this particular cell. It will get the values from the previous cells, the previous gates. It will calculate its candidate value. It will immediately say calculate the candidate value. And it already have a memory, some memory associated with it. नहीं, exploding मतलब मैं उसको बड़ा करके दिखा रहा हूँ, गुलजार. So what I'm saying is the prediction that should come from this cell depends upon the activation value, right? And that activation value will help you to get the y value, right? Y of t. If you're passing x of t, right? If you're passing x of t into this cell, which is you're passing this word into this cell and to do some prediction. Okay. Whether your model is learning that this particular word means, say, singular or plural, whatever. So you need to do all the computations here based on the input and whatever the model is sending from the past knowledge. You generate an activation value, and that is further used. The whole game is about this activation value, right? The whole game is about this activation value, this value, the state of this particular cell. So GRU does not say that, okay, you calculate that 10H value, which is this, and say, okay, directly use that. No. It says there are certain parameters that helps me to update and reset this value. And how can that be done is controlled by certain other gates. So if this is my candidate value, C of tilde, so this is my C of tilde, which I know how to calculate, which we have discussed. So there will be an update gate, which is a sigmoid function, takes a value mostly either 0 or 1, but sometimes in between. I need to, when I'm doing these calculations, this is multiply. This is not plus. This is multiplier sign. Okay. So what I want to do is, I want to see कि भाई आपके अपडेट गेट की वैल्यू मल्टीप्लाइड बाय द करंट वैल्यू जो इस सेल की है, 1 minus of the update gate and whatever is coming from the outside. That actually, so means this and this both will help me to decide this value. And how to calculate the update gate, we also know that, because update gate में भी आपका क्या जा रहा है, यहाँ से अगर आप देखें x of t, which is the input at the time t, c of t minus 1, c of t minus 1, अब यहाँ पर a को c बोल दिया, as in the value which is coming from the previous cells, the knowledge which is coming from the previous cells. Okay, so that's another thing. And then the weight vector. So this weight vector actually, because this is in the vector form, but you will understand that there will be a separate weight for this and a separate weight for this, because separate weight for this, separate weight for this. This is just a weight vector and then a sigmoid function. So you will get the update value. So now, अब अगर आप लोग एक चीज ध्यान दो, रीसेट गेट को भूल जाओ, अभी एक चीज को अगर ध्यान दो, अगर मैं पहले सेल से स्टार्ट करता, पहला सेल, फिर दूसरा, फिर तीसरा, and then so on, like so, the values which are getting passed, right, the values which are getting passed, for example this value, it was computed from the previous value, just previous, always, but there is a contribution which is added from the previous while passing it to the next. So that contributions keeps moving ahead. Here the contributions keeps moving ahead. That's what the differentiating factor is, which was not happening in a simple RNN. Simple RNNs were just computing this using definitely the previous values, but they were not, after computing this, they were not further adding, multiply this, further adding that more contribution of the previous state. So that's what is the difference here. So these previous states will keep getting accumulated when they go to the next stage. Okay. So that's what the differentiating factor of GRU is. Definitely you are calculating candidate state using the previous state, but after calculating you are also adding that previous state to it. So क्या होगा कि C of t में C of t minus 1 का कुछ contribution आ गया, फिर C of t plus 1 में C of t का कुछ और contribution आ जाएगा. तो अब यहाँ पर आप previous contributions को ignore नहीं कर रहे हो, rather उनका भी कुछ component लेके चल रहे हो. कितना वो component important है, वो आपकी अपडेट स्टेट, आपकी जो सिग्मॉइड वैल्यू आ रही है वो बताएगी. ओके. कई केसेस में ऐसा होगा कि आपकी करंट स्टेट किसी काम की नहीं है, जैसे मान लो जब आप इसकी बात कर रहे हो, ओके, जब आप इसकी बात कर रहे हो तो इसकी कोई कंट्रीब्यूशन इस लेवल पे नहीं चाहिए हमें. इन जनरल आई एम सेइंग it ate, who ate, cat ate, what it ate, it may ate something and now it's full. Okay, so the model will understand when it learns through multiple cycles that this may be more dependent on this rather than this, but this is how the previous contributions keeps getting added and accumulated for your model to learn. Okay, there is another gate which is reset gate, which also works in the similar way, which is like if you go back here, So if you look at reset gate, it's also getting the hidden state and the input of x of t. So input of x of t, hidden state, which is c of t minus 1 or h of t minus 1, multiplied by their corresponding vectors plus the bias for the gate, sorry, for the reset gate, this one for the reset gate. ठीक है, तो आप देखेंगे तो फॉर्मूला ये वाला और नीचे वाला फॉर्मूला सेम ही है, कोई फर्क नहीं है, सिर्फ वैल्यूज बदल गई। वैल्यूज भी कौन सी बदली हैं, सिर्फ वेट्स बदले हैं, सिर्फ वेट्स बदले हैं, सिर्फ वेट्स एंड बायसेस बदले हैं। ओके, that's one thing. But now when you get this again, the reset, what happens is this reset, if you look here, if you try to build a correlation, so this reset gate will calculate some value again between 0 and 1. Yes, yes, hidden states means what is coming from the previous state, and इसका अपना खुद का होगा, आप कह सकते हो मेमोरी सेल, वो अगली स्टेप के लिए वो भी हिडन स्टेट ही माना जाएगा। तो इवन हर एक सेल की खुद की एक हिडन स्टेट होती है और एक प्रीवियस हिडन स्टेट जो उसके पास आ रही है। तो एक तरह से हिडन स्टेट इज नथिंग बट जो उसकी मेमोरी में, उसकी करंट मेमोरी में इंफॉर्मेशन है, तो इसका एच ऑफ टी होगा। तो दिस रीसेट वैल्यू will further be multiplied with the hidden state value before it get passed into the candidate state. So if you look here, so this candidate state means now what it's saying is you're getting something from the past. Okay, you're getting something from the past. How important it is, like 0, you don't use it to do any resets. 1 means you want to do the resets, and who will help you to do the reset is again the past value. So is the current value enough, like is x of t enough for getting the candidate state, or the past hidden state really helps me to reset, to do the resets? Then how much will that be important? This seems similar, this word seems similar, but they have considerable difference, so that's getting multiplied here, which is nothing but symbolized here. Okay, so that's what your reset gate is doing. Okay, so this is about the group. Read about this article, try to understand more. So so far we're talking about vanilla RNN. Vanilla RNN मतलब जो plain RNN था. Now we are talking about group. Okay, तो RNN के अलग अलग types हैं. Whether you are talking about vanilla RNN, which was like the simple RNN, or you talk about group, or then you talk about LSTM. Okay, so just read this. I'm just expanding it a bit. So guys, please read from here till here and try to understand it. I'll give you, you have 1 minute, try to understand. Sorry. So Nishta, just comprehend this, and then we'll take a break. So guys, we'll connect at 12 o'clock. Takes a 15-minute break. But the important question here is the value of RT when it is 1. It's like vanilla RNN. When it's 0, it's like a MLP. You should know about these things. When these values are zeros and ones, what that model will actually behave like. And for anything in between, it's like a group. But extreme values say what that model will become. Okay, like in regularization, when I talk about regularization parameter, and I will say if the penalty parameter is 0, that means it's linear regression. If it's not, then it's like ridge or lasso, like that. So you should know these things comes in written exams, and you should know this. Okay. Okay, extreme values where your model is behaving like a older model, a simpler model. So we'll take a break. Let's connect at 12 o'clock. Guys, if you are back, please ping me, and if my screen is visible. Guys, am I audible? My screen visible? Okay, perfect. Okay, so just to summarize this, the GRU thing is, देखो, RNN or vanilla RNN was just looking at the short-term relationship between the sequences, not the long-term patterns. To understand or read the long-term patterns, GRU or LSTM came in picture. And if you look here, how they are working is, ultimately it's all about the hidden state, which is like coming from the previous cell, and the input state. Now everything is controlled by these two, which is the reset and the update gate. So reset gate simply tells you कि ये जो hidden state आपके पास आ रही है वो आपकी short term dependency है, right? Because just past, तो उसका क्या कितना इंपॉर्टेंस मुझे लेना है, शॉर्ट टर्म डिपेंडेंसी. अपडेट गेट क्या कर रहा है कि आपका जो भी कंप्यूटेड आउटपुट आया, जो कैंडिडेट आया, राइट, ये कैंडिडेट को एज इज यूज करना है या इसको बिल्कुल भी यूज नहीं करना, सीधा सीधा हिडन स्टेट को यूज करना है पास, या दोनों का कॉम्बिनेशन. तो अगर आप दोनों का कॉम्बिनेशन लेते चले जाओगे हर बार इसमें थोड़ा थोड़ा h(t-1), तो वो आपके पास आगे प्रोपोगेट होता चला जाएगा, तो एक लॉन्ग टर्म रिलेशन बनता चला जाएगा. तो दिस इज व्हाट अ GRU और a gated recurrent unit is. A gated, as in you have certain gates which are controlling the short term and the long term dependencies between a sequence. Recurrent units, yes, because these are recurrent neural networks, RNN cells. So these are gated recurrent units. So now with that we come into another area which is also similar, or I would say same, the LSTM or the long short term memory. Now where this is same and where it is different. So let me try to show you with this thing. Okay. Okay, this is a bit small, so let me. Okay, so if you look here in the LSTM, which is another RNN, long short term memory, ये भी जो आपके वनीला आरएनएन के प्रॉब्लम्स होते थे कि वनीला आरएनएन जो है वो शॉर्ट टर्म डिपेंडेंसी पे काम करता है, लॉन्ग टर्म पे नहीं करता, वेनिशिंग ग्रेडियंट डिसेंट के प्रॉब्लम होते हैं, वो सारे सॉल्व करता है लॉन्ग शॉर्ट टर्म मेमोरी. लॉन्ग शॉर्ट टर्म मेमोरी is even bit matured form of GRU. I would say it's more matured as compared to GRU. In what sense? It contains 3 gates. Okay, so if you look at here, there is a forget gate, there is an input gate and an output gate. So let's talk about what's the difference. So here also what you are doing is you are using the input value and you have a hidden state. But here we also introduce one more term. We will introduce one more term. What is that? That is the memory cell. So you have a hidden state, but here we introduce one more term which is memory cell. So there is another value which is a memory value. We will talk about it. So here from every past stage you will pass on 2 things. One is the hidden state value, one is the memory value. We will see that. So here the difference is you have 3 inputs. As such, you have 3 inputs, and then you have 3 gates. No, Nishtha, 3 inputs: the memory state, the hidden state, and the actual input, which is the word. So along with that word, आप past cell से कुछ knowledge लेना चाहोगे यहाँ पे. That knowledge will be some sort of like vectors or values like between 0 to 1 or -1 to 1. ये वो values होंगी. But now see how it works. So first of all, you are passing some data from the previous cell, and also you are passing some input. Everything is going inside forget gates and output gates, which are again your sigmoids. Sigmoids means value will be between 0 to 1. Here this is 10H, value between -1 to 1. But again here we will have a candidate state or a candidate memory, we will say. So here we will say it's a candidate memory, C of T. So we, using 10H, we compute candidate memory here, not candidate state. Okay. So first of all, we are calculating a candidate memory. Using that candidate memory and output gate, we will calculate the hidden state, H of T. समझ रहे हो? तो यहाँ पर भी मेमोरी और हिडन स्टेट आ रही हैं, तो यहाँ से भी मेमोरी और हिडन स्टेट निकलेंगी. लेकिन यहाँ फर्क ये हो गया कि आपका 10H फंक्शन आपको हिडन स्टेट नहीं दे रहा है, आपको मेमोरी दे रहा है, मेमोरी स्टेट, which is another parameter. Okay. So first of all, you are getting a candidate memory, and using candidate memory, we will get a candidate state, or rather the final state, whatever it is. या कैंडिडेट स्टेट तो होती नहीं है, या कैंडिडेट मेमोरी होती है बस, और कैंडिडेट मेमोरी को यूज करके आपकी एक्चुअल मेमोरी और एक्चुअल स्टेट निकलती है. तो यहां से आपका सी टिल्डे निकलेगा, सी टिल्डे, और फाइनली दैट विल बी यूज टू कैलकुलेट सी एंड ऑल्सो एच. ओके. सो पहले तो इन्होंने LSTM मॉडल में मेमोरी और हिडन स्टेट ये दो अलग अलग, दोनों को अलग अलग कर दिया. पहले क्या होता था, ये एक ही होता था. हम कहते थे कि मेमोरी के अंदर हिडन स्टेट की वैल्यू पड़ी है, दीज वर सेम. बट नाउ दे आर सेइंग नो, वी विल यूज 2 सेपरेट वैल्यूज फॉर मैनेजिंग लॉन्ग टर्म डिपेंडेंसीज. सो सेग्रीगेटिंग दीज 2 सेपरेट वैल्यूज helps them to manage the long term dependencies in a better way. Now how that is achieved, first of all, look at this forget gate. So forget gate is what? Forget gate is like whether the thing which is coming from the past, should I keep it, should I forget it? That's like this. मतलब जो past memory है, क्या मैं उसको याद रखूं या भूल जाऊं? Simple, right? Forget or keep, 0 or 1, and anything between 0 1 is like intermediate. थोड़ा सा याद रखो, थोड़ा सा भूल जाओ, like that. Input gate says whether the input which is coming should be considered or not at this level. Means there is some word, whether that word is really important for this context or not. If it is not, I will not give any weight to input. I will make it go away again between 0 and 1. So that's input gate. But then input is going through the input gate, input is going into 10H. So अगर input 10H में जा रहा है, तो 10H तो मेरे को input की वैल्यू दे देगा, मतलब जो कैंडिडेट मेमोरी की वैल्यू है. लेकिन क्या रियली ये जो इनपुट आपने कंप्यूट किया है वो इंपॉर्टेंट है? वो कैंडिडेट गेट कंट्रोल करेगा यहां से आके. कैंडिडेट गेट विल कम फ्रॉम हियर एंड विल कंट्रोल दैट, द इनपुट वैल्यू. सो candidate is going to control that. Here it's getting controlled by input gate. Now you will say no, I'll use something from the past, something from the current, then the sigmoid values will be between 0 and 1s, and then those values will come over here from here, and they will calculate the candidate memory. Not the candidate memory, sorry, the final memory, not the candidate memory, final memory. So candidate memory will come from here. And now again, the older memory which I have, will it play any role in this particular thing? Or if yes, then how much part it will play will again be controlled by this forget gate. So this forget gate is sending this particular value over here. And now using this candidate memory, I will pass it to the output gate, again a sigmoid function, and I'll get h of t. So that's how it will work. So let's try to go into the formulas. So we'll start with the hidden state and the input state. We will just keep passing these values because these are the two most important values. We will pass it into the forget gate, input gate and output gate, and we will compute this. The input at the time t, the forget gate at the time t, and output at the time t. Between 0 and 1, their value will come. But now I'll calculate the candidate memory, and the candidate memory will definitely depend on the input that I'm passing on and the hidden state. Okay, consider that there was no initial memory. Even then your model will start, right? So that's why you still don't have the past memory here. It's just the candidate memory which I'm computing. So candidate memory will be computed again in a simple way. X of t having some weight with this, h of t minus 1 have some weight with it, and then the bias, and you calculate the candidate memory. But now this candidate memory which you have calculated, you need to account into this the memory from the past. Okay, and that's what forget gate will help you to control. How? So far we have done this much. We got up till this place with our candidate memory. But now this is the past memory. This past memory is going to come and add into this plus sign, right? It's going to add in. And this is a multiplication sign, element wise dot product, kind of element wise multiplication. So from forget gate, I am going to get some value which is going to control the level of importance of the past memory, and then it will just come to this formula. And now we have to understand this formula. Yeah, Gulzar.
अरे जो ऊपर जो फॉर्मूला लिखा है सी टी इक्वल टू का, तो मल्टीप्लिकेशन साइन जो डॉट है वो मल्टीप्लिकेशन साइन है.
हाँ, बट वो एलिमेंट वाइज मल्टीप्लिकेशन साइन है. नॉर्मल मतलब ये स्केलर मल्टीप्लिकेशन नहीं है, ये वेक्टर मल्टीप्लिकेशन है.
वेक्टर, अच्छा.
तो वी विल अंडरस्टैंड दैट. Okay.
Okay, sir.
So this multiplication is nothing but this symbol. Okay. So this is like f of t from here, c of t minus 1. They are multiplying here, right? So this one. And then there is this plus symbol, right? So this plus symbol is this, right? And what is this? This is the I of t value which is coming from here, and candidate memory coming here, and this is again a multiplication, right? So which is this term. Getting it, Gulzar? Clear? कि ये प्लस इज दिस प्लस एंड ये क्या मल्टीप्लीकेशन हो रहा है वो ये वाला है और ये जो मल्टीप्लीकेशन है वो यहां से आ रहा है. Gulzar, is it clear? The formula versus the representation, the visual representation. Okay. So now let's understand this. What it says is forget gate, right? So forget gate can have extreme values between say 0 and 1. So when it's 1, how it should behave is, if you look at, if the forget gate is always approximately 1, if this value is 1, this is directly controlling what? The past memory. The past memory cell CT-1 will be saved over a time and passed to the current timestamp. As in, if this value is 1, if the forget gate value is 1, that means you are not forgetting. You're not forgetting. Okay? If it's 1 means you're not forgetting what the past value was. But if it's 0, you will forget it. So since we are not forgetting it, that means that value should come here. तो अगर इसका ये मैं मेमोरी सेल बना लेता हूं और ये मैं इसका हिडन स्टेट बनाता हूं, तो क्या ये वैल्यू इसके मेमोरी सेल में आनी चाहिए? तो अगर ये 1 है तो ये यहां आ जाएगी. ठीक है, ये यहां आ जाएगी. लेकिन अब क्वेश्चन ये है कि जो इनपुट गेट है उसकी वैल्यू क्या है? अगर इनपुट गेट की वैल्यू मैं 0 कर देता हूं तो ये 0 हो जाता है कंट्रीब्यूशन करंट स्टेट का. दैट मीन्स द पास्ट मेमोरी विल कीप प्रोपोगेटिंग फ्रॉम वन सेल टू अनदर. गेटिंग इट? मतलब जो वैल्यू यहां थी, मान लो यहां वैल्यू थी 0.05. So here also the value will be 0.05 because I am saying input gate is 0, means input gate को ऑफ कर दो. मतलब जो भी इनपुट में वैल्यू आ रही है वो किसी काम की नहीं है. जो पास्ट स्टेज था that is enough. ओके, तो इस सेल में कोई नई वैल्यू नहीं आएगी सीटी की, रादर सीटी will be same as C of t minus 1 because the forget gate is 1 and the input gate is 0. So these kinds of questions again comes in numerical or MCQs, like you will be given the value of C of t minus 1, H of t minus 1 and X of t, and they will tell you given the value of forget gate is 0, input gate is 1, what should be C of t? Similarly, some other scenarios. तो आपको वो जो सिनेरियो होंगे वो ऐसे नहीं होंगे कि आपको पेन पेपर लेके मैट्रिक्स मल्टीप्लिकेशन करना है, वो लॉजिकल होंगे. ओके, तो if you can logically think, they will give you some options that okay, C of t will be completely dependent on C of t minus 1, it will be completely different from it, some kind of that things. So they can give you 4 options, right? H of t will be same as H of t minus 1 or not. Yeah, so C of t minus 1 is the memory state and H of t minus 1 is the hidden state of the previous cell which was at the time t minus 1. तो अगर मैं कहता हूं कि like lazy cat for example, again lazy cat, so lazy ये एक न्यूरॉन में गया होगा, कैट इसमें गया होगा वर्ड. तो अभी हम कैट के लिए कंप्यूटेशन कर रहे हैं, लेकिन लेजी वाले से एक मेमोरी वैल्यू और एक हिडन वैल्यू दो निकली होंगी. ये वो है यहाँ पे अभी, राइट? ये पूरा सेंटेंस है उसका, ये पहला वर्ड था, ये दूसरा वर्ड है, तो ये दूसरे वर्ड के लिए हम सारी वैल्यूज कंप्यूट कर रहे हैं. ओके, नाउ since we calculate this, So in GRU, if I talk about, you normally don't talk about a separate memory term. You only talk about the hidden state. Okay, there are no such two things. So this is one of the another difference, that here we only talk about like these two states, whereas in GRU we were talking about the hidden state. Okay. And there the output was directly this 10H output. In GRU, like 10H output was there, and on top of that we were doing some more calculation. If you look here, there the candidate state that we used to have, right? The candidate state that we used to have, we used to put in a particular formula, this one, the update state values and the candidate state values. This we were doing, but our AT and CT were same. Okay. So CT is your memory, the memory cell, and AT is your hidden state. Just remember that. So they are both were same, but in LSTM they haven't kept them as same. There are separate formulas. So if like someone asks you to draw a parallel between GRU and LSTM, so what happens is this C of t is more equal to the formula, the calculation that we were doing in the GRU. Okay, this part here is additional actually, which we are going to talk. But in GRU, this was the final output that we were looking at. This thing here, this thing is additional. Okay, so this used to be what we used to calculate in GRU. So what we used to do was, the candidate memory that we have, we were comparing it to what? The previous memory. Whether the previous memory is going to be coming as is here, right? Whether it's going to come in as is here, or it will be of no use and just the new computed value will come here. All those kind of decisions are also being taken here. But here the formula is bit different. There only update gate was helping us to take the decisions. Here we have two gates, the forget gate and the input gate. Okay. Here there the update gate was kind of telling us like how much should be the importance of the past value. But here it's like the two separate gates are actually controlling the things, because if you look here, if you look here, it was like one gate which was talking about both the current, the importance of the current, and the importance of the past. But in the LSTM we don't do that. We say that whatever is the input gate here is like the update gate. Okay, so here the input gate is like the update gate. So the input gate will only control the current state, but the previous state will be controlled by a separate gate, which is the forget gate, to segregate the two operations completely. and then you will get to the current memory cell value. Okay, so that's the biggest difference. There you were having only one gate, which was the update gate, which was controlling current in the previous states. Here we are saying no, let's have a update gate separate and a forget gate separate to control these things. Okay. I have one doubt. I would request you guys to look it further on internet, and I'll also share the material. I need to check whether this value and this value, they should be swiped, as in whether this should come here and this should go here. So I'll also check, but I think you guys also please check that. यहाँ पर तो it's correct, but here I think there is a confusion whether this should come here and this should come here, because then the logic will completely change. How update gate is controlling the current state and the previous state, right? So just check it. Don't take it as is जो image पे दिख रहा है, कई बार वो misprints हो जाते हैं. Okay, so that's another thing. But what I'm saying is, if you have to compare these two, so if you compare these two, I'm saying this is your update gate and this is your forget gate. Okay, so this is the update gate and this is the forget gate. So here you have this separately as a forget gate and an update gate. वहां पर एक ही गेट दोनों काम कर रहा था, एक में इट्स लाइक प्रोबेबिलिटी एंड एक में लाइक 1 माइनस प्रोबेबिलिटी, इस तरह से. तो गुलजार मैं ये कह रहा हूं कि बस इतना चेक कर लेना कि मान लो ये x है और मान लो ये 1 माइनस एक्स है, ठीक है. तो मैं ये कह रहा हूं कि शायद ये x नहीं है, ये 1 माइनस एक्स होना चाहिए, और ये 1 माइनस एक्स ना होकर ये x होना चाहिए. एक बार ये चेक कर लेना. मैं भी आपको जो एक्चुअल रिसर्च पेपर है वो शेयर कर दूंगा, rather than checking on the internet. There is a research paper by these people. I'll share with you. उसमें सबसे सही होगा, ठीक है, क्योंकि फिर पूरा मतलब बदल जाता है. Okay. And after that, the final thing is that we have here is an additional term, which is the activation. So this is the activation value at the time t, which is the actual output from this model. And that is given here like this. The actual output from the model will be, output gate will generate a value, and then there is again a element wise multiplication. This C of t will be here, right? So it's like 10h of C of t. Okay. Now why all these things are done and all, guys, and these are all the points of research. You have to go through the detailed documentation, why they have done all these things. I'm explaining you to a particular level, not beyond that. So now what's happening here is, so that you can explain this to someone and you can understand this when you read it, these things will not become difficult for you. Okay, so now if you look at, this is the candidate memory, or rather I would say the final memory. Candidate memory तो यहाँ पर थी, ये final memory है आपकी. This final memory, you do a 10h again on that, जो भी value यहाँ से आपकी निकलती है, and on that you will apply element wise operation with this to get h of t. So the formula for that is shown here. If you look at the memory cell, you take a 10h on that, and then you do a element wise multiplication with the output gate, whatever it was. So ultimately output gate का नाम output क्यों है? Because it's actually giving you the output. which is the activity or the activation function. So for every cell, there is output value, which is actually the hidden state, which is the most important part of it. But here we have segregated these separately, the memory state and the hidden state. That's what the difference is, and that's what the formulas are here. Now again, important thing to read this, please. Whenever the output gate approximates 1, we effectively pass all the memory information through to the predictor. Okay. But can anyone tell me if the output gate is 1, then is C of t and H of t same? Are they going to be same? If output gate is 1, is C of t and H of t going to be exactly same numerically? Or they will be different? Why? Why they won't be same? Yeah, Nishtha Didi, you are correct. They will be different. But why? They can't be same. But what is that? What is the relation between CT and ST? If your output gate is 1, what is the relation between CT and ST? So I'm saying if this output is 1, then the CT is going as is here. Then CT and ST should be same, right? But if I'm saying this dot product things, they are 1, all 1, 1, 1, 1, 1, this vector, and then whatever vector I'm getting, say from here or the value, if this is all 1, you multiplied anything with 1, you will get the same value, right? So if CT passes through this gate and this gate is 1, CT and ST shouldn't be same. CT is passing as is to HT. What is HT? It's coming from CT. I'm saying OT is 1. There is one missing thing. You guys are correct, but there is one missing thing that you're not telling me.
Excuse me, sir. सर कि XT और tan CT सेम होगा ना, पर CT पर XT और CT तो डिफरेंट हो सकते हैं.
Okay. Yeah. So that's what. Yeah, Aditi, you are also correct. So the point is, I'm not passing CT here. Yeah, Gulzar, correct. I'm not passing CT here. I'm passing it via a 10H, right? So CT and HT won't be same, even if the output gate is 1, because CT is getting transformed through an activation function. So if CT is, say, a numerical value, any numerical value, and then you have this HT, which takes values between 1 till -1, like -1 till 1, that means this value will be between -1, somewhere between -1 to 1, right? This value will be somewhere between -1 to 1. But this value, what can be the possible values here? If you look at sigmoids, so here you are getting a sigmoid. Sigmoid can give you a value between 0 to 1. But from here also you are getting a sigmoid of 0 to 1, which is also getting a dotwise product. and also it's getting added to this. So this can be a continuous number which is having the addition of sigmoid values from here and then values from here. So it can be a bigger number also. But this will be between -1 to 1. This will primarily between 0 to 1. Primarily between 0 to 1, but it can have some other values also. You have to check that. Sigmoids will give you values between 0 to 1. 10x will give you the values between -1 to 1. Right? So understand that these two values, HT and CT, they will not be same. They will be different. And what this particular statement is speaking here, just read this, okay? If the output gate is close to 0, if output gate is 0, you retain all the information only within the memory cell. Means if output gate is 0, this value means you have whatever you have will be the memory cell value. There won't be any value here. So there will be no hidden state value for this, because you are saying I don't want to generate any output hidden state. Just the memory cell value is enough for me at this particular stage. And those value will get passed to the next step. Like, look, if you look here, so if you look at this, let me make it bigger. Yeah. So if you again look at here, we are doing the same thing. We have a forget gate, we have an update gate, we have a 10H gate and an output gate. So the memory value is coming with the forget gate. You have this inputs, right? So it's exactly the same thing which is happening. But what I'm saying is, if you look at the next layer to which we normally pass the data, the next layer to which we pass the data, I'm again saying you, ये क्या है? ये जो सेल है, ये अपने नेक्स्ट सेल को भी इंफॉर्मेशन पास करता है, राइट? टाइम t0 पे, t1 पे, t2 पे, t3 पे, that will be like this. But here I am generating the actual output, and to generate the actual output I don't need the memory state. What I need is the hidden state. So if you don't have the hidden state, there won't be any further processing at that level, which is what this thing is saying. That does not mean that your model will stop. That does not mean that your model will stop. Model will still propagate the information. But what it's saying is, at that cell, you had to say predict something. That prediction cannot happen because your A of t is 0, or rather output gate is closed. So nothing will be passed on to the next layer. Next layer as in the one which is above it. But what we are saying is, still this kind of processing will keep happening, because this is the same neuron or the node at time t0, t1, t2, t3. So you will keep passing on the memory and the hidden state to the next steps. but at the same time, this side of processing will not happen whenever this value is coming to 0. Okay, that's what something important. So I'll share these links and all these documents with you. Go through it. Just few corrections here when I share this document. If you look here, it's missing this 10h function. So that's why I have mentioned it here. Okay, so here it's missing this 10h. That's one thing that you need to take care. Second, which I told you, in this we will look whether the update gate and 1 minus update gate, they should be swiped. Okay, when I share this document, okay, this is you should remember. And the third thing that you should remember is this is not a plus, rather this is a multiply symbol. तो जब आप ये डॉक्यूमेंट्स अगर मेरे रेफर करोगे, ये मैंने मतलब आई टुक इट फ्रॉम वन ऑफ द फेमस कंटेंट फ्रॉम एंड्रयू एनजी. So this plus should be this. Okay. There is one more thing which is LSTM are also of multiple kinds, but we are not going into that. So there is something known as a peephole. There is a peephole connection LSTM. The peephole collection LSTM, but the difference that comes here is it becomes more complicated. It becomes more complicated in the sense that the gate values which you are calculating, right? The gate values which you are calculating, in all of these, the gates were never, see, you are never ever using this in any gate level computation. You're never using the memory. You're only using the hidden states at the gate level computations. See, so the LSTM never uses the memory state, rather it uses the hidden state at the gate level computations. But do I really need to pass on this information also here? If I pass on that information, what it will be? This multiplied by its weight plus this multiplied by its weight plus this multiplied by its weight. So forget gate will work on the memory also. So this is another area of research. All these are deep research areas. So this is not yet used much commercially, but this is another model, because since I have memory, I'm definitely using this memory in the computation of this A of t here, right? Here this hidden state is definitely being computed because of the memory, but गेट कब खुलने हैं कब बंद होने हैं ये भी मेमोरी का कंट्रीब्यूशन होना चाहिए, प्रीवियस मेमोरी का ऑब्वियसली होना चाहिए, but then your calculations will become mathematically more complex and system will become slow. You need more computation power. So that's one of the problem with peephole connections in the LSTM. But definitely opening and closing of the gates should also be decided not only by hidden state but by the memory state also. So that's where these things are. Okay, so read about these because it will take some time to comprehend. You have day till tomorrow. Do this. What's this? Okay. Yeah, Gulzar, you are asking something.
भी आपने जो किसी की वैल्यू 0 का जो हाँ था अभी इस स्लाइड से पहले अभी।
हाँ हाँ
सर एक बार वो बात फिर से बता दो जरा।
ओके 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 so before we do that, uh, I'll tell you, Gulzar, okay, let me just summarize it for everyone. So RNNs, we know unidirectional RNN and bidirectional RNN. Can anyone tell me what is bidirectional RNN? On a concept level, what is bidirectional RNN? I'm talking about vanilla RNNs, plain RNNs, unidirectional and bidirectional. What is bidirectional RNN? So, Gulzar, I'll tell you that also, but please answer the questions. I'll ask few questions uh, before we conclude for the day. Take previous as well as the next values into consideration. Absolutely gated ones. No, Karan. Aditi, yeah, you are correct. Bidirectional RNNs are the one that takes not only the previous but the next values also in consideration while uh, learning a pattern. Okay, that's what happens in that particular case. Now, okay. Okay, that's fine. So now there are different kinds of RNN architectures. Okay, so tell me an example. Like there is a big article and I want to summarize it. Like I have a 10-page article, want to convert it into a 1-page summary. Which RNN architecture should it be? One to one, one to many to one, many to many. Yeah, Vipul, correct. Aditi, correct. Anyone else? Yeah, Gomini, correct. Okay, okay. Now, given a movie script, I want to know whether it's about a romance, it's a romantic movie. What is the the context of it? What will it be? Whether it's like uh, this horror or whatever. So it's like many to one. Okay, but can a movie fall into multiple categories also? Like it may be comedy and horror both. That think about it, right? It can happen. So it can again be a many to many. So this field of NLP is like that only. But you put a condition that no, I want only one as an output, and you build architecture of many to one. Then even if your model find out more categories, there will be some confidence level. तो जो highest confidence वाला level होगा वो आपको बता देगा, because आपने उसको बोला भैया many to one. But अगर आपने many to many वाला architecture implement किया, then it will tell you multiple with level of confidence. Okay. For example, you do entity, you do part of speech tagging, right? मैं कुछ बोल रहा हूँ, part of speech tagging करते हो, right? अब कई बार कोई ऐसा वर्ड हो सकता है जो पर्सन को भी रेफर करता हो, प्लेस को भी रेफर करता हो. मान लो किसी का नाम है दिल्ली. आई एम सेइंग दैट Delhi went to Mumbai. Very weird example, but yeah. If you look at this context, here Delhi can be a person or can be a place. But now, looking at the context and also the future data, bidirectional RNN you need, right? You need a bidirectional RNN. Otherwise, your model, if unidirectional, will always say that Delhi is a state. But when it runs a bidirectional RNN, it will say no, Delhi is a person. So understand that kind of scenarios and read more about it. Coming to GRU solved the problem of vanilla RNNs where they were only learning the previous patterns or sequences, not the past. So GRUs were solving that. How they solved it, we saw that. There are certain gates, update and reset gates, which were introduced. And here the memory state and the hidden state are same. So if you look at the hidden state and the memory state are same. But LSTM says no. I will have these are separate. I will have these as separate memory state and a hidden state. Hidden state will be used to compute the gates, right? Mainly the forget gate and the update gate, but not the memory state. Memory state will be used only to compute the final hidden state. Okay, the final hidden state from the model with the help of the value which is coming out of the update gate. But none of the gate was using the memory, even not the output gate. Right, guys? Output gate is also not using the memory state. It's this multiplication gate, this multiply gate, which is using the output gate का जो output है और जो आपकी memory state है, right? Be very clear with that. So can we build a model where the gates uses the memory state also along with the hidden state? Yes, that kind of LSTM will become peephole connection LSTM. That's why you see here that computations will become more heavy mathematically, but it is still the simple things. It's just weighted sum. So these values will also be passed here. It will be passed here. It will be passed here, like that. Okay. So that's what actually happens. And Gulzar, what I was saying is, I'm asking you, what can be the possible values of this and possible values of this for that? And can they be same? Two questions, right? First, they cannot be same because C of t पे जब 10 of h लगाओगे, so these whatever this value will be, it will get transformed between -1 to 1. So that's what 10h function will do. So first of all, these two values can never be same. Your hidden state will always be between -1 to 1. But again, you can change this activation function to other functions. But this is what these researchers have done a lot of work and identified these to be the best. 10h. So these values cannot be same. That's what I was saying. And एक minute. And if you look at this curve, that NH curve takes the values between, it's also like sigmoid function. It's also like sigmoid, but different because can anyone tell me sigmoid or 10h में क्या difference है? If you look at the screen, the values are between -1 to 1. So 10h takes the values between -1 to 1, whereas sigmoid takes the values between 0 to 1. So उसका जो curve होगा, yeah, it will be like this. It will be crossing like this. वो ऊपर रहेगा, मतलब यहाँ से ऊपर जाएगा, ठीक है? But if I shift this, I shift the sigmoid curve down, it will become 10h. It's just shifting it from 0.5 to 0. So that's not sigmoid, that's 10h. So wait. So Gulzar, is that fine? Yeah, Harshita,
Yes, sir,
correct. Mm-hmm.
दैट्स फाइन कि सिटी और एसटी तो डिफरेंट ही होगा, पर उस फंक्शन में जब आपने में tan h सिटी और एसटी तो सेम हो सकता है, क्योंकि अगर जो वन वैल्यू जिसको आपने बताया था उस फॉर्मूले में, जब
हाँ, आप क्या कह रहे हैं? आप कह रहे हो
एच टी और सीटी तो डिफरेंट होगा, पर क्या एच टी और टेन एच सी टी सेम हो सकता है अगर ओटी वन है तो?
हाँ, वही बट
ठीक,
10 of ct will become h of t ना।
यस सर।
बट ये सारी चीजें वेक्टर लेवल पे हैं, तो यू हैव टू कंसिडर ये सारी वैल्यूज ऐसे नहीं है, ये स्केलर वैल्यूज नहीं है, दे विल बी वेक्टर्स, दे विल बी वेक्टर वैल्यूज like 0 0 0 0 0 0 1 like that. So these are all vector values. So when you read about it more, you will get to know. So you have a day. Let me see if there is any more question. 1 minute. So yeah, Vipul, very good question. So that's what I'm saying. Vanilla RNNs, unidirectional, bidirectional, whichever, they look up to a one level past value, right? One level ahead or back, right? Not too much in the past, right? Gulzar, question is above that only. Vipul's question I'm asking. I'm saying are LSTM and GRU equally efficient, right? So first of all, we know when not to use vanilla RNN and should go with LSTM and GRU. Now the question is, out of these two, which one is better, right? So there is no such answer whether GRU is better or LSTM is better. Both are equally good. The only point is GRU are simpler to comprehend, understand, and explain. And computationally, they are not that complex or heavy. And GRU came in recently to make things easy. LSTMs are equally powerful or even somewhat more powerful, I would say. LSTM are somewhat more powerful, but the problem is a trade-off. They become computationally very heavy. However, the research is going on to make sure that GRUs and LSTMs are equally good, and GRUs will become the industry standard instead of LSTM in the upcoming times. So there is no right and wrong answer to it, Vipul, but yeah, that's a very good question, and that's what you guys should read more about to understand the difference between LSTM and GRU. Okay, so go through it in detail. You will understand about it that everything here is a vector, no scalar values. How those vectors are being passed. One second. So look at this. So here guys, if I am saying this is a layer, right? This is a layer, for example, to which you are passing on the inputs. Okay, say you are passing input characters. This was actually you passed HELL, and maybe you are asking for the next word. I'm just giving you an example. Okay, so if you are training a model to predict key, it's a word correction. For example, you are building a word correction algorithm. So what will happen? You will pass a word and then each character you will pass H. It will go here. There will be some weights, and then the output layer will say the next word is E. You pass E, it says, oh, next word is L. You pass in, it saying you the output word. And now if your dictionary contains the words as like article contains hell most of the time, then it will say, oh no, it should be hello, because the next word which it has learned is O. Given this input, the next word should be O. But this can only be done if you have learned the past sequences of characters in that words, right? So what I am saying is, your model does not understand or will never understand what is H. मॉडल को H क्या है नहीं पता. मॉडल समझता है ये 10000, which is a vector. So which is a vector. So I am saying the data which we pass on is a vector. Okay. इसको आप अगर हमारी नाइव बायस वाली प्रॉब्लम से कंपेयर करें, वहां हमने क्या किया था, हर वर्ड को एक फीचर बना दिया था. मान लो वर्ड, मैं यहाँ लिख रहा हूँ वर्ड है ABC, मान लो ये वर्ड्स थे हमारे स्पैम और उस वाले केस में. तो अगर किसी ईमेल में ये एक वर्ड है तो हम उसको मतलब नहीं है तो 0, है तो 1, नहीं है तो 0 ऐसे कर देते थे. तो ये क्या बन जाएगा, एक तरह से जब ये वैल्यूज फिल होती चली जाती हैं, राइट, तो ये 0101 के आपके पास वेक्टर्स बन जाते हैं यहाँ पे. ओके, so understand this, that the NLP problems, whether you are working at the word level or the character level. Character level मतलब spelling correction, and word level मतलब मान लो कुछ भी language translation. तो वहां हम जो न्यूरल नेटवर्क्स हैं उनको कभी ये वर्ड्स नहीं देते, हम उनको वेक्टर्स पास करते हैं. विद दैट प्लीज रीड इट इन डिटेल, understand it. Okay, and in the next class we will take one example of natural language processing, maybe machine translation or missing word prediction or spell correction. Any of these three, we will take any of these three, whether spell correction, missing word prediction in a sentence, or maybe machine translation, anything, and we will implement it. But I request you guys to read more. This is a very detailed field. Okay. No, Vipul, I'm talking about natural language processing, na? RNNs. Image detection, I will talk when I will talk about CNN. तो अभी तो आज का पूरा दिन इसी में ही चला गया ना. तो अभी Thursday I will still continue with RNN, and Friday I will start CNN or image detection. Okay, so that will be part of CNN. CNNs or GANs. These are for image detections. Okay, guys. I hope I was able to make it simple for you. Whatever I can make it. Please read it more. It's not that simple actually. Okay, read it more and understand that we are not passing words or characters. We are always doing vector and matrix level multiplications in this entire scenario. Everything is vectors, weight vectors, input vectors, and output vectors. Everything is like that. And this output vector then further signifies what particular word it should be, and then model predicts that okay, this vector should be this word, that kind of things. Okay, so I want you all to go thorough in detail of these RNNs. Okay, if no more questions, we will end this class today. Okay, please try yourself using Keras how to do machine translation, because जितने भी Kaggle competitions हैं अब सब NLP पे ही होते हैं. Image detections या language processing ही होती है Kaggle में. पहले होते थे structured data पे, अभी Kaggle competitions are on deep learning mostly. Okay, guys, thank you. Thanks a lot. Read about Kaggle competitions, few Kaggle competitions, and get to understand what they are asking. Okay. Thank you.